CSA.
Hey, everybody. My name is Alex Merced. And what we're talking about today is about unifying data for data applications with the data lakehouse. So basically, by the end of this presentation, the hope is that we'll understand one, what is the data lakehouse? Two, what are the sort of challenges with like modern sort of data applications? Whether we're talking about building a BI dashboard, agentic AI applications, what are the typical bottlenecks that we find in building some of those applications? Okay. But before we get down to all of that, let me introduce myself. I pushed the right button. Now I think what did I do? Oh, I did push the right button. Oh, see what happened? Quick fun story is I lost my previous clicker. But see, this clicker is weird because it's vertical. So usually I think right, left, you hit right to go to the next slide, but up and down, not quite as intuitive. Okay, UX, good UX. Okay. But I'm Alex Merced. I'm the head of DevRel at Dremio. Basically, I've spent the last 4 years of my life basically talking about the data lakehouse. Okay, not talking about just what the data lakehouse is, but open source technologies around the data lakehouse, like Apache Iceberg, which I've written a book on, Apache Polaris, which I've also written a book on, and Apache Arrow, which I have not written a book on. But I've done that. I've basically spoken at many events, mostly in the data space. So I speak at like that's just most years. Spoken at Data Council. I'll be at the Data Streaming Summit next week in San Francisco. I spend a lot of my life talking. But also I was a software developer beforehand. And, a lot of times I like to still like make fun stuff on the weekend. So like one weekend I was bored and created a document database in JavaScript just because why not? And that was CoDB. So that's a thing. And I've written a couple books. So these 2 books you can get for free. Just scan this QR code and you can get those 2 books for free. Get a nice free PDF and learn all about some of the things that I'll talk about during this presentation in great depth. Okay. And literally, we just released the complete manuscript of Apache Polaris Definitive Guide like yesterday. So that's right off the bus. And then my 3rd book is where you see the stickers on the chairs. So if you're interested in the 3rd book, which I'm about 2 chapters away from finishing, that's that book there. Okay. So now, I'm raffling away a free copy. So again, this will sign you up for a raffle to get a free copy of this book because there's no free copy to that one right now. But I'll put those QR codes back up at the end. And now let's kind of get on with our teacher presentation. Now, what is a data application? What is this thing that we're building? What is this different than other applications? Okay, and since a data application is going to be one that basically is specifically interacting with data, whether it's for operational tasks, analytics, decision-making, the idea is that we are focusing specifically on interacting with data that already exists versus creating new data or creating experiences for the new data. Okay, this is an example like a BI dashboard. If you ever use something like a Tableau or a Power BI, applications that fuel that, or creating custom visualization applications, basically embedding analytics like a dashboard in another application, agentic AI systems, whether you're creating like a CLI to do like Claude Code, or you're creating like a chat interface, like ChatGPT's interface, whether you're creating any of these kinds of tools, they're going to be working with data. Okay, so you're creating an application on top of a variety of data. Okay, but bottom line is that when you're working with data, you're going to want low latency. You want to be able to get that data fast. You want to make sure you have, especially for a lot of like nowadays, you're talking about enterprise-wide analytics, where basically, hey, I want to join all my different departments' data to kind of get a full picture of the whole company. I'm going to want unified data, which is a little harder than it looks, especially at bigger organizations, as I'll talk about in a little bit. And 3, well, we don't want to accidentally expose like the wrong information to the wrong people, so you want that data governed. Okay, and doing all of these things on a growing amount of data, in growing amounts of places becomes more and more difficult every day. Okay, so and again, nowadays our data is in a bunch of different places, scattered across places like databases. So these are your transactional databases where you're doing all your transactional type workloads. Like adding a user, subtracting a user, adding an order, subtracting an order, or updating an order. These kinds of transactions where you do with like Postgres, MySQL, so forth. There's data warehouses. These are more optimized for analytics, where I'm saying, hey, give me the average purchase for every user in Nebraska. Okay, and that's a more complicated question where I'm taking every row and only taking a few columns of those rows and running analytics. It's optimized for those types of workloads. These are your Snowflakes, your Redshifts, your BigQueries, these types of systems. Then I have data in data lakes. What's a data lake? Well, the data lake is the idea that instead of actually having a system like a database or a data warehouse, how about we just store the data as files in like S3 or ABLS or whatever, cloud object storage you prefer. And usually we use formats like JSON, CSV, Parquet. You store the data there and you use tools, including tools like Dremio, to run analytics directly on those files where they're at. That's an option too. But now I have all this data stretched across all these different places. Okay. And again, each of them has a unique way to access them. I have to set up separate access controls in them. So I'm creating users in Postgres saying, hey, they have access to this. I'm creating users in Snowflake. They have access to this. I'm creating different access control rules for my different users in S3, and S3 access policies are always a lot of fun. And so forth and so forth. It gets complicated really quickly. Creating several different calendars. One, credential sprawl. The more different data sources I have, that's more credentials that are going to be in my application, which means more security issues, because if I forget to use the wrong environmental variable or I committed to version control, oops, I've exposed chunks of my security. Okay, so ideally, the less credentials I have to expose to my code, the better. Okay, data silos. The data's in so many different places. You might have different software development teams in different departments of the company. And now I need access to this data that's part of another department. And now I have to put a request to them. Hey, can I get access to the database that you guys run? And now you're waiting like 2 months to get access to them because they have other things they're prioritizing, and that delays what you're trying to do. So your data gets basically siloed off for you to actually complete the projects you're trying to complete, which slows everything down. So it's not even just like the access, how fast you can pull the data, but just your ability to get access to the data in the first place. Okay, and then performance management. Okay, those actual queries, you want them to run fast. So normally we would manually do things like, materialized views, but then we have to do all this manual work to maintain those materialized views and make sure that they're in sync and refresh periodically. They might be doing BI cubes, or you're talking about like aggregations. There's all these different things we can do to optimize the performance of those queries. But again, at scale, it gets trickier and trickier and trickier. Okay, so let's talk about how we can move towards a direction if you're building these kinds of data applications that minimizes these problems. Okay, so first we're going to focus on minimizing the data access issue, the silos. So one of the patterns you're starting to see a lot today, the pattern I'm spending all my time talking about, is the pattern of a data lakehouse. Now, in the world of a data lakehouse, what happens is you have this problem where you have different departments in the company, and all of them, you end up with one of two scenarios. Either you have one central data team that manages all the data infrastructure for the whole company, but then what happens is anytime any department needs anything, they have to go through that team. And now that team has been backed up with a bunch of requests all across the company, thus waiting a long time for those requests. The second scenario is each department creates their own data platform. Well, now one team is using Redshift, another team is using Snowflake, another team is using BigQuery. Problem is, those things don't all talk to each other very nicely because they all store the data differently, they all work with the data differently, all optimized for their particular system. So now you're not just doing ETL, extract, transform, load, basically moving the data into the data warehouse. Now you're moving data between data warehouses, which requires you to write more code. You have to test that code. You have to deploy that code. You have to troubleshoot that code. And you have to pay to run that code. Okay, so you're increasing costs, increasing development time, increasing the time before you get the data. And things can still go wrong, which means the actual ending project might still be not perfect. Okay, and again, if you make bad decisions because you have bad data, well, now you're being counterproductive. Okay? So this is sort of like the world of today and yesterday. Okay? Well, what you're starting to see a lot of companies do, especially at the large enterprise level, but it's becoming more and more accessible down different size enterprises, is this platform of a lakehouse. The idea is, how about we don't put all of the data into a data warehouse? Because again, then you end up with a situation where every team has like a different system that doesn't talk to each other. You have silos. What if we just standardize and say, hey, we're going to put the data in the same format that all these tools can talk to? Because the problem is, if you try to standardize and say, hey, we're all going to use the same tool, everyone has a preferred tool, right? So then you start getting into this political warfare saying, hey, we like Redshift, we like Snowflake, we like this. Okay. And then someone's going to win and it gets better and, not fun. What if everyone can keep using the tools they like, but they can work with the same copy of the data? Okay. We separate the storage and the format of the data from the tools you use to access the data. Okay, and that's what this lakehouse paradigm is. So the idea is the data will be stored as data files. So I mentioned earlier a file format called Parquet. Now, Apache Parquet is really good for analytics because it's a binary format, which is going to be much smaller. It stores the data in a columnar format, which is going to be much better for compression, much better for analytics. So it's a very good, compressed, fast way to save the data. The problem is Parquet files, they only know what's inside the file. They don't know about the other files. The problem is I might have a data set that's across like 1,000 or 100,000 files. So my sales table might be 100,000 Parquet files and they don't know anything about each other. So this is why we want to wrap it in what's called a table format, which is a layer of other files, metadata files, that give context around, hey, these are the files that make up the table. This is the schema of this data set. This is the whole data set. And that's what we get. That's where the metadata files come into play. So we have data files, the Parquet files. We have an open table format that allows tools to see those Parquet files as a table, like in a database. And then we need a way to track those tables to catalog them. Now, these are things we take for granted because when we use a database or data warehouse, that just is part of how it works. Like you just go into Snowflake or you go into Postgres and just knows what tables you have. How those tables are stored behind the scenes, you never think about. It just is. But in the data lakehouse world, all these things are broken apart, done separately. Okay, so I save the files, I have metadata around those files, and I have a catalog. But the beauty of it is now, if one team is using AWS, they can connect their tooling in AWS, query those tables. Someone else is using Snowflake, they can query those tables. Someone else is using Microsoft and they're using like Azure, they can query those tables without none of the data having to be moved or duplicated and all the costs that are associated with it. Okay, so that's what the Lakehouse pattern is. It's essentially saying, let's all store the data in a uniform way so that way all my tools can talk to it. This is going to minimize your costs, save you time and having to share data between departments because everyone can use your preferred tools, but everyone can access the data without having to copy it. Okay, and then you're going to have much more consistent data across teams. So that's like the first step. Okay, ideally, like you move into a lakehouse, and now most of your data is now in a central format that any tool can access. Wonderful. You've broken down many of the silos, but you haven't broken down everything because you don't have control over all data, right? Sometimes you get data from third parties that might be in a third-party database or data warehouse. You might have some other files that, CSV dump that you dump from some platform you use. Like if you just dump files from now Salesforce has a way to natively do this, so you don't have to worry about that with Salesforce, but other tools will just dump you a bunch of CSV files. So before I get into solving that particular problem, let me just get a little bit more into that whole like table format thing. So again, this is just a visual illustration so you can see what I mean by a table format. The idea is that I have these Parquet files, the data files. Right now, before we add the metadata layer, they're just files. Okay, so technically, to me, I know these 4 files are my sales data set. I know those 4 files are my order state. But my tools don't know that. And they have no way of magically knowing that. But when I wrap them in metadata, okay, so now that metadata turns these groups of files into a table. Now, when my tool, something like a Dremio, Snowflake, whatever, goes and looks at the metadata, it knows, hey, this group of files is the sales table. This is the schema of the sales table. And now I can interact with it in the same way I could interact with a table that's in Postgres or in Snowflake, whatnot. Okay? It just basically changes the way my storage, we should turn any storage system into a database, essentially, that any tool can talk to, which is really cool. Okay? I mean, I find it pretty cool, but I guess it's my job then. But I do find it cool. That's why I've been doing this for so long. Okay. So now getting back to basically solving the silo problem. So again, you have your lakehouse. So your lakehouse, again, is all that data stored in like your object storage as of like an iceberg table. So iceberg, just to clarify what iceberg is that metadata format. So while Parquet are the data files, iceberg is the metadata around those files that tells it, hey, these files are a table. Dremio is a platform that's specifically really built for like Iceberg. Like it's natively built to give a native Iceberg experience. Most tools have Iceberg support. Like you use Snowflake. Snowflake does Snowflake, but it also does like most tools also do Iceberg. We're like the one platform that's like natively like you were built specifically for that. But one of the things that we do that's going to answer the problem that you have with having all this data elsewhere is we also connect to anything else. You can connect to your Snowflake for all your other Snowflake tables. You can connect to Postgres. We can connect to on-prem data sets like a Hadoop or a Hive. So basically, instead of having to put all those different credentials in your application, so instead of your data application having connection, like all this connection code for a Postgres database, for your data lake, your databases, your data warehouses, all this code, juggling all those credentials, you just connect them to Dremio, okay, or any other federation engine. So we're one of 2 federation engines. There's not like 1,000 of them. But the idea is that we can federate your data, meaning connect different data sources. And now all of that, now you just connect to Dremio. And when you connect to Dremio, now you're only putting one set of credentials in your code. And that set of credentials only has access to what you gave it to. So it doesn't have access to all your Postgres tables. You can decide this set of credentials has access only these Postgres tables. Read or write, access to these Iceberg tables, access to these Snowflake tables. So that way you can create credentials that are scoped to your particular application. And then again, you can always just swap them out afterwards. So you only have one set of credentials you have to worry about putting in your code to a platform that acts as kind of a middleman. So that makes it, and also this makes the performance thing a lot easier. Because oftentimes when you're doing joins across different tools, what would happen is like, okay, I would go pull in this one data set from Postgres, and then I would load that up as like, let's say JSON, let's say I load it up as, let's say JavaScript was a JavaScript object or an array of objects. And then I would load up this other data set from, let's say, MySQL, and I would load that up. And now I have these two arrays of objects in JavaScript memory that I'm then doing operations with in memory, which is going to be a much more heavy duty way to do it. You're loading up much bigger objects into memory, doing operations that probably shouldn't be done because you're pulling the data from different places. Versus you can actually have all that processing, all those queries, all those joins, all that stuff happen beforehand, across these different data sets. You can design those in Dremio and those get loaded up into a much more optimized format, much more performant, and then you're just getting the end result. So your code becomes a lot simpler because you're not doing all that cross joining across system in your code. You're just pulling the already pre-curated, pure, ready to go data sets. And Dremio has its own automated caching layer where automatically will caching based on your query patterns. So in that case, all those materialized views you would have to manage, you don't have to do that anymore either. So your code gets a lot simpler and a lot more secure. So you can focus on building what is the experience that the user should have with the data, not focus on having to spend so much time wrangling how do we access it. So having a data lakehouse at all, having the data like Apache Iceberg tables, one, breaks silos across different tools, but then when you use a tool like Dremio, then it can help bring in the rest of your data that might be accessible to you as well. Okay, so the idea here, this makes building your application, and there is a open source community edition of Dremio that's free. So you could seriously just spin up a free container of Dremio, connect all your data sources there, and then build your application just using that as your sort of funnel for all your different data sources, which is a lot of customers do. They'll literally just build full applications on top of them. And then a lot of people who use Dremio never realize they're using Dremio because under some abstraction, it's abstracted away in the applications that are built on top. Okay. So again, we have zero ETL federation. So again, this is helping you unite your data because basically you can connect all your different data sources right through Dremio. A big thing with agentic AI. So that's a big topic of conversation these days, right? Agentic AI. Because it's a really good application of AI. It's nice for me to be able to have a tool and say, hey, can you go look up all the customers and send them an email today? Okay, that's pretty practical, pretty useful. The problem is LLMs, just because they have access to your data doesn't mean they understand your data. Okay. They know that you have an orders table and they know you have this other table here, but they may not know which columns to join it on. It may not be obvious to it. So this is where a semantic layer comes in. Semantic layer, which could either be built into a product. There's other people who will do like just a semantic layer that's just independent. Companies like Cube and AtScale. But what it is, it's a layer that provides additional context on those data sets so that when the LLM, your agentic AI, is going in there and like figuring out, hey, what SQL should I write to send over? It's going to get the right SQL more of the time. It's going to be more deterministic because you've given it the information to do so. So we have that built in as a wiki. But again, there's also independent semantic layers that can be, like in Python, there's this new library called like Wine Semantic Layer. There's companies again like AtScale and Cube. Dremio, we have one that's built in. But the idea is that you're going to want a semantic layer between the data and the LLM or your agent, because you want your agent pulling in those additional semantics on top of the data to have that additional context. So again, this is just another way that we help make it easier to build data applications by providing those semantic context for your AI use cases. Originally, semantic layers were built before agentic AI. They were built because humans wouldn't know what to join data sets on. So the idea was, can I predefine a lot of these typical ways we're going to use the data as a view or something like that? And the funny thing is, like, most of the practices of good data stewardship that were good when we were trying to build the data directly for like other people to write SQL queries are just the same. They're just magnified now in the world of agentic AI, because you have to imagine agentic AI is a human with a much less context than an individual. So you have to be extra careful about all these details because they're not going to have the context that an individual can make up for. Okay, I can maybe halfway do my modeling, halfway do my semantics, and then, someone who understands the business enough can maybe fill in the gaps. But now, all these practices are same things we were doing before, but they're not just more important because we have to fill those gaps into these AI tools. And again, real-time virtualization is meaning that instead of having to make copies and copies of every possible data set, you can just join data sets in Dremio or any federation tool right there in the tool. and then have those definitions, and people will just query the views. And then again, it'll use a caching layer under the hood to make sure that performance is good. Okay. And again, we have the whole minimizing credentials. So again, since Dremio is going to be handling all the credentials for your different sources, in that case, it's not in your code. And then you can programmatically access Dremio in any programming language. We just do JDBC, ODBC, we have a REST API, and we also have a protocol called Apache Arrow Flight. Let me talk about that for a second, because that's something useful to know. It's another open standard. So there's another project called Apache Arrow. So remember I mentioned like, hey, the alternative is we do a lot of this juggling of data in our code. So if I'm doing it in JavaScript, I may be loading the data as like, again, arrays of objects. And those are going to have a certain memory footprint, okay, which probably won't be optimal. There's a effort to create a universal way of representing data in memory called Apache Arrow. Actually, the project partially started at Dremio, or way back in the day when it started. So essentially, the idea is that this format is going to allow you to store a lot more data in memory in a lot smaller amount of space to operate on it. It's all like optimized to make sure that even within the memory operations, you're not duplicating the data too much. So it's really fast because you're really optimizing how you represent the data in memory. But the problem is, what if you send the data to another computer? You send it over the network to some other piece of software. Sure, I just process the data really fast. But as soon as I use JDBC, ODBC, I have to turn the data back into rows, not columns, which means I have to spend all this time converting the data and then converting it again on the other side. So that project, the Apache Arrow project, realized, that's not a good idea. Let's create a new protocol that keeps the data in the same format as it travels. So you use this really fast format, and then you actually send the data via a protobuf in the same format, so that when it gets to the other side, there's no serialization. And there's a video you can find on YouTube where I actually compare like PyODBC versus Arrow Flight. With like 1,000 records, you're not going to notice a difference. There's just so few records. The time it takes to serialize and deserialize is nothing. But when you're talking about like 1 million records and you start getting to really substantial amount of records, it makes a huge difference in the time that it takes you to, because the query might be really fast, but the time it takes you to actually process the data on the other end adds up when you're serializing that many records. So that's why we have that protocol. Nowadays, it's becoming an industry standard among data processing tools. So like Snowflake has an Arrow Flight endpoint, InfluxDB has an Arrow Flight endpoint, becoming more and more of a thing. And then they've created a whole new protocol called EDDC that's like the JDBC for this kind of data. So it's a cool thing. Okay, and again, I've written lots of stuff on this. So later on, I'll put the image for my podcast if you guys want to hear me talk more about all these things. I talked a lot. And again, basically, we're reducing risk of operational work, because the idea is like the more that a platform like Dremio can do the data handling, then the less you're doing your code. Now you're just, if you're building like a LangChain agentic AI application, then all I have to do is really, like nowadays we have, everyone's familiar with MCP at this point, right? I mean, I know, but I take a look at the agenda. I was like, okay, there's a lot of MCP discussion here. Good. Okay. So bottom line is that MCP allows us to kind of create like little pockets of reusable AI functionality. Okay. So in that, Dremio, of course, like everybody else, has built an MCP server. So basically nowadays, you build an agentic application, you just connect to Dremio's MCP server, and now your agent has access to all of Dremio's tools and semantics and all that without you having to build all that in there. And now, literally within minutes, you can have someone type in, actually I do this like every other week I do a workshop. Please budget for a workshop so you can get hands-on with this stuff. It's a lot of fun. And I get to hear me talk more. These are the jokes. But what happens is that, again, it's just becomes a lot easier to do a lot of stuff in the code because, again, Dremio is picking up a lot more of the work. And then, we provide as tools like our MCP server, again, makes connecting these things much easier. Okay. Again, we have this caching layer. It's called Reflections. It's really, really cool. Definitely don't have enough time to get too deep into it, but I could spend literally an hour just talking about this and how this works. It's essentially like a materialized view on steroids. So if you know how a materialized view works, and you know of all the problems with materialized views, like how to refresh them, having to tell people to update their queries, to use them, all these kinds of bottlenecks, we address all those things in a really interesting way. But I have done talks on that, so you can find those on YouTube, just for the sake of time. We have great optimization for like iceberg tables, because another thing about the Lakehouse to keep in mind is that when you're saving your data on like S3 as tables, well, it's not like a database. Database under the hood, like Postgres, Snowflake, they are optimizing the data that you stored in there constantly. That's why the software is always running. That's why the database software is constantly running, because it's constantly optimizing. Now you don't have that. Now it's just a bunch of files on a storage somewhere. So in this case, it's on you to kind of optimize the underlying storage of files and make sure that, hey, I don't have too many files with just like one record. We automatically optimize those files for you. So that way that becomes a thing you don't have to think about. But then again, it starts getting like using a data warehouse or a database again, because you're not thinking about distancy. So it's an interesting architecture, but again, we try to take a lot of the edge. If you're doing a data lakehouse, we take a lot of the hard parts out by handling that part for you. Okay, but bringing it all together, theoretically, bringing it all together, you have Apache Iceberg that allows you to standardize data on the lake so that we have one place that has your data that all your different departments can work in. So all your departments kind of standardize and saying, hey, we're going to use whatever tool we want, but we're going to end up making a copy of the data in